In exercise 9, we're going to graph several functions. This is a list of some very basic functions that you really need to memorize. You should be able to draw these by hand, and yet you definitely can use a calculator to help you get some of the values for these points, especially when things get messy with the square roots and cube roots. And the textbook calls these the toolkit functions because a lot of what we're going to do later in the course is going to involve variations on these basic functions. So if you know the basics, it makes it a lot easier to understand the variations and transformations that we're going to talk about later. And we haven't said too much about domain yet, but most of these functions have domain all real numbers. In fact, there's only one below whose domain is not all real numbers. We'll talk about that when we get to it. So let's go ahead and start graphing each one of these. And again, you can hop ahead if the first few are obvious to you. But I'm going to go through each one. And I have these on, I have my graph paper already for me. And so the first one is f of x equals negative 2x plus 6, that you should recognize as a linear function. You should be aware that this is of the form mx plus b, where the b value is 6, which is the y-intercept of that graph, and the m value is negative 2. That's the slope of that line. And it helps to think of slope as a fraction. So if you get an integer value, you can always write it over 1. And so I'm going to graph this line using the y-intercept and slope values. And so I'm doing this from scratch. So I'm drawing my axes. Again, graph paper really helps as things get more and more complicated in this course. Now when you set up a graph, you should label your axes. You should label your scale that you're using for the graph. I'm just going to label 1, 2, 3, 4, the 5. So that is just a way of saying that each square is worth 1 unit. You can change that scale if you have to in certain situations. I think here this will work fine. So I know my y-intercept is 0, 6. 0, 6 is a point on the graph. All right, that's right there. I got 1 point. And then one way you can get more points is just by plugging in, of course. And you can also get more points by using the fact that the slope is negative 2 or negative 2 over 1. You can think of that slope value as representing vertical change over horizontal change. So sometimes people say rise over run, or change in y over change in x. And so a vertical change, I'm going to start at this y-intercept point, and I'm going to go through a vertical change of down 2, and a horizontal change of positive 1 is going to take me to another point on that graph. And I can do this over and over again. From this point I can go down 2 over 1, down 2 over 1. Now, of course, I could have just plotted some more points, but this is one way, and it's kind of important to know you can use the y-intercept and the slope alone to sketch a graph. There's that line. And I guess one other thing I wanted to say about this briefly is that this function notation, this is the same as saying y equals negative 2x plus 6. So we are going to use function notation more often, but that's, oops, I guess I went a little higher. There we go. All right, so we got one line drawn. That was we call that a linear function, right? second example, B, f of x equals 3. This is the same as saying y equals 3. So this is a very simple example, but weird, that maybe is worth talking about. If I were to set up a table of values for this function, now with function notation, instead of writing x and y, we can write f of x in the second column. What this formula is saying is no matter what I plug in for x, I'm just picking some numbers at random here, I'm always going to get output of 3. This is something called a constant function. So if I set up my axes here, x-axis, y-axis, label my scale. I mean, you don't have to label the 5, just make sure it's clear what each square represents. And if I plot these points 0, 3, 1, 3, 2, 3, 3, 3, they're lining up. I'm getting a straight line graph. It's a horizontal line graph. Again, also called a constant function. And you may be familiar with the fact that any equation of the form y equals a constant has a horizontal line as its graph. And, okay, third one is a graph we've already kind of mentioned, but let's go ahead and go through some values here. Maybe I'll take -3, -2, -1, 0, 1, 2, 3. We're just squaring, right? -3 squared is 9, -2 squared 4. These are positive y values. -1 squared 1, 0 squared 0, 1 squared 1, 2 squared 4, 3 squared 9. And I think I may overlap my other graph a little bit. That's okay. I need a lot of y values here. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. X, Y. My x-axis is just 1, 2, 3. Same in the negative. And my 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's my y-axis labeled. And let's plot these points. -3, 9, -2, 1, 2, 3, 4, -1, 1, 0, 0, 1, 1, 2, 4. We get that beautiful bilateral symmetry of the parabola, right, of the graph of a quadratic function. This graph is symmetric around the y-axis. There we go. So that curve is called a parabola. The graph of a quadratic function. I think a U-shaped curve that you're already familiar with. Okay, so we've gone through our first 3 toolkit graphs. Maybe we'll do one more here in this opening segment, and then I'll switch to another video. Let's do x cubed. Now, x cubed maybe is not obvious to folks, but let's once again set up a table of values. So if you're not familiar with the graph, you should be able to plug in. And I'm going to start with the positives, work my way in the opposite direction. So 3 to the third power is 3 times 3 is 9 times 3 is 27. 2 to the third, 2 times 2 times 2 is 8. 1 to the third is 1. 0 to the third is 0. -1 to the third. Now a negative number to the third power is negative. So I'm going to get -1. -2 to the third is going to be negative. I get -8. -3 to the third is going to be negative 27. Okay, so now to graph here. So this is a good little example of where we might want to change our scales a little bit. I'm going to call that 0. X-axis, I'm fine with just 1, 2, 3. So there's my 0, 1, 2, 3, negative 1, negative 2, negative 3. But on the y-axis, let's see here. I want to try to fit these values at 27. If you're really stuck, you can use a whole sheet of graph paper, go 27 squares up, 27 squares down. But I think what I'm going to do is I'm just going to do this. 5, 10, 15, 20, 25, 30. So as long as you're consistent, that's fine. You don't need to use the same scale on the horizontal and vertical axis, which you can see I'm not doing here. And now I'm going to plot my points. I get 0, 0. Now 1, 1 becomes a little bit difficult to plot on this scale, right? It's really, really close to the x-axis. 2, 8, okay, that's going to be about there. 3, all this was to make room for 3, 27. And then I have negative 1. Negative 1 is also going to be very close to the x-axis below. Negative 2, negative 8. And negative 3, negative 27. And so the graph, this is called the cubic function, has this sort of squiggle to it. It looks something like so. It's worth noting that the cubic function has origin symmetry. It's also a one-to-one function. I think when we mentioned one-to-one functions, we had this example. So you want to be able to generate this picture fairly quickly. So I'm going to stop the video here. We'll do the rest of the functions on a separate video, rest of the graphs.